This schematic illustrates a multi-axis machine tool. Equipment like this serves as a benchmark for modern motion control, coordinating high-precision movement across the X, Y, Z, and B axes. The precision and power required by these individual axes are driven entirely by AC servo motors. Industrial environments subject these motors to extreme mechanical violence. A stamping press slamming down into solid metal generates repetitive, high-frequency shot weights that travel directly back into the motor's driveshaft. Specifying a servo for this environment involves reconciling a strict matrix of thermal limits, mechanical constraints, and electrical variables. For our engineering case study, we will look at the Indramat Mac AC Servo series. This lineup scales from the compact Mac 063 designed for tight spaces to the high-inertia Mac 111 built for massive loads. Correctly matching a motor's physical parameters to a machine's duty cycle ensures basic electromagnetic rotation can withstand the rigors of industrial architecture. This illustration shows the physical baseline of a Mac motor. You can see the thick, totally enclosed outer housing sealing the internal magnetic components. These motors are rated IP65, an ingress protection standard indicating an enclosure is completely dust tight and protected against jets of water, which is mandatory to block the coolants and metal dust found in machining centers. The output shaft emerging from that sealed housing comes in two primary designs. Engineers use plane shafts for non-positive, friction-based connections, and shafts with keyways for form-fitting hub connections. Sealing the motors so tightly creates an immediate engineering hurdle. Continuous start-stop operations generate severe internal heat, and that heat has no direct path to the ambient air. The baseline cooling state for these motors is natural convection, where heat radiates out from the casing into the surrounding air. Natural convection is only sufficient for standard low-intensity duty cycles. Extreme repetitive loads dictate the use of active surface cooling blowers. Adding these blowers introduces strict geometric constraints to the machine's overall design. When longitudinal space along the shaft is limited, engineers specify radial cooling. This places the blower directly under or to the side of the motor. If the machine profile is narrow, axial cooling mounts the blower in line with the shaft. This keeps the width tight but adds significant overall length to the assembly. The choice of thermal management geometry directly dictates whether a motor survives a continuous heavy-duty cycle or suffers thermal failure. While the mechanical housing protects the motor, the feedback loop acts as the critical sensory mechanism that dictates its ultimate precision. At baseline, all Mac motors feature an integrated tacho feedback system. This handles continuous speed evaluation and basic rotor position recognition. Standard tacho feedback covers most applications, but precision lathes require a high smooth run quality variant. This specialized tacho is wound specifically to minimize residual torque ripple during rotation. Achieving exact positioning control requires a structural modification. The motor must be expanded with an accessible second shaft end, providing a mounting point for an external encoder. This table provides a general comparison of encoders. Engineers choose between the two primary external feedback options listed here, incremental encoders and absolute encoders. Incremental encoders use multiple optical slits on a rotating disc to output speed pulses. Because they only count changes in the rotation angle, they require a manual return-to-origin operation upon power-up. A return-to-origin operation is a calibration process where the machine moves back to a known zero point so the controller can re-establish its coordinates. Contrast this with absolute encoders. Because absolute encoders constantly detect the exact physical position of the motor axis, they retain 24-bit position data even during a total blackout. They require zero restart calibration when the power returns. However, standard optical encoders contain fragile glass discs. Subjecting these to the violent shocks of heavy punch presses will cause the internal discs to shatter. To solve this, engineers must specify the shock-damped mounting encoder variant. This mechanical isolation is mandatory to protect the sensor from aggressive shock loads. Selecting the wrong encoder type or failing to protect it with proper mounting limits the machine's recovery speed and durability. If the sensor shatters, the motor's power output becomes unusable. This is a torque speed characteristic curve. This graph acts as the sizing matrix where mechanical, cooling, and electrical capability intersect. The lower boundary is the S1 curve. This defines the continuous operating limit, the maximum torque the motor can output indefinitely while maintaining a safe 60 Kelvin overtemperature at the housing. Above that is the S6 curve, which defines the intermittent operation zone. Operating in this space allows the motor to deliver significantly higher torque spikes than the S1 limit permits. However, running in the S6 zone is governed by a strict on-time percentage constraint. The motor can only sustain these high heat torque spikes for a specified portion of its total duty cycle, typically between 25 and 60%. Pushing into the intermittent zone too frequently without adequate rest forces thermal deformation of the internal components and leads to total system failure. Attaching a surface cooling blower alters this math. Forced air cooling physically shifts both the S1 and S6 boundary lines outward, increasing the maximum load capacity. By manipulating thermal cooling parameters, engineers expand a motor's operational boundary without having to install a heavier, larger frame size. Looking back at the schematic of the multi-axis machine tool, it becomes clear that no single motor type can satisfy every axis requirement simultaneously. For a vertical Z-axis, an engineer specifies a Mach 071 motor outfitted with a closed-circuit holding brake. Because gravity constantly acts on the vertical column, the holding brake is necessary to clamp the output shaft and prevent the tooling from dropping during a sudden power loss. Over on the horizontal indexing table, the load profile changes. This axis requires a high-inertia Mach 112 motor equipped with an absolute encoder, ensuring the system has instant origin tracking for heavy, rapid rotary positioning. To guarantee survival against aggressive, high-frequency intermittent duty cycles in the S6 zone, this Mach 112 must be fitted with a radial surface cooling unit. Mastering the thermal boundary, shock limits, and the exact constraints of the torque speed curve defines the architecture of a highly optimized industrial system.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.